Hello everyone, I'm Akash. In today's video, we will prove that the harmonic series diverges to infinity and the alternating harmonic series is convergent and its sum is natural log of 2. So let's begin the video. We will start with the proof of first. In the first, we have to prove that the harmonic series is divergent and it diverges to plus infinity. So by way of contradiction, suppose that the harmonic series is convergent and it converges to some finite number, say s. Okay, we have assumed the contradiction that this series convergent and it converges to some finite number, say s. Then as s is the sum of this series, so hence we have s is equals to 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 and so on. Okay, but this is greater than 1 by 2 plus 1 by 2, okay, plus 1 by 4 plus 1 by 4 plus 1 by 6 plus 1 by 6 and so on, 1 upon 2n plus 1 upon 2n plus so on. Okay, but this is nothing but this sum is nothing but 1 by 2 plus 1 by 2 is 1, 1 by 4 plus 1 by 4, 1 by 2, 1 by 3 and so on, 1 upon n and so on. So we can see that this sum is nothing but is equals to s itself. So what we get, see that here s greater than s itself, which is a contradiction. Okay, thus our supposition that the harmonic series converges to some finite number must be wrong. Hence, we must have the harmonic series diverges to plus infinity. So this proves the first. This proves the first part. Now let's prove the second one, that is the sum of alternating harmonic series is natural log of 2. To prove this, we will use the convergence of the sequence gamma n defined by gamma n equals to 1 plus 1 by 2 plus up to so on 1 upon n minus natural log of n, that is log n to the base e, is convergent and the limit of this sequence gamma n is defined as the Euler constant gamma whose approximate value is equals to 0.577 something. So we will use the convergence of this sequence to establish the convergence of our series. Okay, so let us write first the nth partial sum of this series. The nth partial sum of this series is Sn equals to minus 1 to the power 1 plus 1 by 1, that is nothing but plus 1. Second term is minus 1 to the power 2 plus 1 by 2, that is minus 1 by 2. Similarly, the third term is plus 1 by 3. Next term is minus 1 by 4 and so on, minus 1 to the power n plus 1 by n. This is the nth partial sum of this series. Now let us consider its subsequence S2n, which is nothing but and so on to okay. Now I can write this subsequence as difference of two sequences as follows. Okay. To see this, clearly 1 is present here. For minus 1 by 2, clearly minus 1 by 2 can be written as plus 1 by 2 minus 1, which is minus 1 by 2. Plus 1 by 3 is present here. For minus 1 by 4, minus 1 by 4 can be written as plus 1 by 4 minus 1 by 2. Okay, and so forth. Okay, so I can write this subsequence as a difference of two sequences, and again after simplifying, when we multiply this by 2, we get, okay, and this first sequence is nothing but log 2n, natural log of 2n plus gamma 2n. So this is nothing but natural log of 2n plus gamma 2n. This is by the definition of sequence gamma n. And this is nothing but natural log of n plus gamma n. Okay. And now by properties of logarithm, log of 2n minus log of n is nothing but log of 2n upon n, and so the answer is log of 2, that is natural log of 2 plus gamma 2n minus gamma n. So when n goes to infinity, this goes to natural log of 2 plus gamma minus gamma, which is nothing but natural log of 2. Because when n goes to infinity, gamma 2n goes to gamma, gamma n goes to gamma, because these are the subsequence of sequence gamma n, and the sequence gamma n converges to gamma, so its subsequence also converges to gamma. So the subsequence S2n of sequence of partial sum converges, and it converges to natural log of 2. Now let's consider another subsequence of this sequence of partial sum, which is S2n plus 1, which is clearly nothing but S2n plus term 1 upon 2n plus 1. Okay. And when n goes to infinity, this, as S2n converges to natural log of 2, this goes to, when n goes to infinity, this goes to natural log of 2 plus 0, that is nothing but goes to natural log of 2. So this sequence also converges to natural log of 2. Okay, this subsequence also converges to natural log of 2. So there are two subsequences, S2n and S2n plus 1. Both are the subsequence of our sequence of partial sum, and clearly these two subsequences are complementary subsequences. So these complementary subsequences are convergent, and they converges to same limit. Hence our original sequence converges to same limit. So this implies the sequence Sn converges to natural log of 2, that is log 2 to the base e. Okay, and as the sequence of partial sum converges to natural log of 2, hence the its series converges to natural log of 2. So this proves the second part. Okay, so if you found this video interesting and helpful, then please like and share this video and subscribe to our YouTube channel. Thank you for watching.